morning. This is the first talk of today. Give me a second. Nowadays, it's all on the internet. So Yanli's song from Washington University in St. Louis, and he will talk about large-time behavior of Laplacians on symmetric spaces.
Thank you. Thanks for having me here. I was a postdoc here 10 years ago, so it's great to be back. And today I'm going to talk about some application of non-commutative geometry and the representation theory. Okay, so let me get started. So the setting is that I will let G to be a subgroup in GL and R. And I assume this one is they connected and closed under transpose. So that is to say, if you have a matrix, if you take the transpose, this matrix still belongs to the group. And actually, this is known as a linear real reductive Lie group, which is one of the main objects where representation theory studied. Okay, so that's K, I will denote it by to be the intersection of G with ON. This is known as the maximal. This is a linear case, but makes sense either. So this is maximal compact subgroup. Okay, so that's in this case we have it's a Lie algebra. It's denoted by little g to be the Lie algebra of this Lie group. This one we have we can decompose it into K direct sum with P. So K is the Lie algebra for this maximal compact subgroup. So this is known as the Gardin decomposition. Okay, so I'm going to consider the manifold I'm going to consider today is something nice. This is known as G mod K. This is a symmetric space. So we can assume this one is a spin. Actually, this assumption is not important if it's not a spin. It's just make its life simpler, so that if it is not a spin, you can always go to the double cover. So that's the point is that if it is spin, we can have this, I will denote by SP. This one is the spinor bundle. Over this symmetric space, say G mod K. Okay, so this is basically a setting. So now I will begin with, let's see, V lambda, I will denote it by this is irreducible representation for this maximal compact subgroup K. And in this case, we can construct, given any representation, finite dimensional representation of K, we can form a G equivariant vector bundle, say E lambda to be times V over K. So this one will give you a G equivariant vector bundle over this symmetric space. Okay, and I will denote this Dirac operator D lambda, because I assume this operator, this manifold is a spin, so this D lambda to be the Dirac operator. Acting on this symmetric space, it's twisted Dirac operator, twisted by this vector bundle. So this is Dirac operator acts on this space, L2 of G mod K of SP tensor with E lambda. Okay, acts on here. Okay, so that's on this space. In fact, on this space we have by the Planck-Charlier. Let me just use another book. By the Planck-Charlier formula, this is how this space are related to representation theory by the Planck-Charlier theorem. We can actually decompose this L2 space, this Hilbert space. E lambda to be as the integral over all the tempered unitary tempered representation of G, and this one will be the H pi will be the representation where this is a space, Hilbert space, where this representation is realized tensor with H pi of star tensor with SP tensor with V lambda, and then I take the K invariant part and I have to integrate. So This one is known as the Planck-Lyell formula, the Planck-Lyell measure. So that this space is, this formula tells you how the Hilbert space and the representation of the G are related. Okay, so that, let me give you one example. Actually, in my talk, you can just, for simplicity, of course, what I said is makes sense for any linear real reductive Lie group, but for simplicity, you can just take this group G to be SL2R. This is non-compact Lie group, and in this case, this K will be SO2. Okay, so for this group, it's Temperdue, what it look like. So it will be, it has, for this non-compact Lie group, it's if you are interested in its representation, Temperdue, then it consists of two parts. One is the continuous part. The continuous part consists of two lines. This is known as the spherical representation of G. This is the non-spherical representation of G. So this Planck-Lyell measure is some very interesting information we wanted to detect. So I will just write down the Planck-Lyell measure for this special case. So for the spherical representation, which is parameterized by this half line, so it's the Planck-Lyell measure is given by S times hyperbolic 2S over pi. Okay, so this is the Planck-Lyell measure for the spherical representation. So this is the mu pi over there. And for this non-spherical one, this is given by S of hyperbolic cotangent pi S over 2. So this is the Planck-Lyell measure for the two family of continuous representation of G. And in addition to this continuous family, we also have discrete series, whose Planck-Lyell measure is given by 1, 2, 3, and so on. So that is to say, there's always a pair. This is a holomorphic discrete series. This is a anti-holomorphic discrete series. Its Planck-Lyell measure is given by 1, 2, given by Z. So this is known as the discrete series representation of G. This is what is the Temperdue of SL2R look like. Okay, so that is to say, with this, if you know the representation of SL2R, you can really have a nice decomposition. You know on which space it acts on. Okay, so now let me tell you the background where the motivation of this. Oh, I forgot to mention this is a joint work. With Shu Sen and Xiang Tang, my colleague. Sorry, I should say this at the beginning. Okay, so that's the motivation of our project is that background is the theorem by, this is a very classic, I think it's maybe 40 years ago. This is Tia Schmidt and later generalized by Kohn-Moscovici. So what they prove is that they actually, on this symmetric space, they really compute, because we have a Dirac operator, say d lambda, they really compute the L2 index of this d lambda. Actually, they compute it and they obtain a topological formula. So in the work of Tia Schmidt is that they assume this group, non-compact group G has a co-compact the lattice sitting inside this G. So you can quotient by the lattice, you can get a compact locally symmetric space, so that you can apply the L2 index to compute the index on a compact manifold. And what Kohn-Moscovici generalizes to, they just compute the von Neumann dimension or von Neumann trace for this Dirac operator d lambda, because although it acts on a non-compact manifold, but it has a G acts co-compactly. Okay, so that's what they showed is that when this lambda, V lambda, where lambda is the highest weight for the K representation, when lambda is regular, I will define or talk about regular. What here, just to think about, I'm not going to give a definition of a regular now, but later I will tell you what do I mean by a regular. So if it is a regular, then what they showed is that this index is non-zero. So if it's non-zero, it means that its kernel must be, there's something contribute to the kernel. In fact, this one implies the existence of a discrete series representation of G. So what they computed is that this one, let me write down the formula because I will get back to this number, this formula later on. So this one will be alpha belongs to all the roots for G. This is you choose the positive root system for G, and this is O alpha, and lambda is the highest weight plus rho K. Rho K is the half sum of a positive root for this compact, maximal compact subgroup K. Okay, so in this case, this is what they computed. And what does this mean? Because this is some information. If you use this Planck-Liouville theorem, we can tell in priori this comes from representation theory for this G. So what do you compute? So this one in fact equals 2. If you use this Planck-Liouville theorem, we can tell is that this is equals to the dimension of this part. Star tensor width. It's actually V of lambda plus rho n, I will explain, times mu pi. So what they showed is that if lambda is a regular, there's only one discrete series representation will contribute to the index, actually contribute to the kernel of this Dirac operator. And also for this one, this space, this SP may not be a irreducible. Actually, it won't be a irreducible representation for K, but what will really contribute to the index will be the one with the highest weight given by rho n. What is rho n? Rho n is the half sum of the non-compact root, because in this case we have a compact root, we have a non-compact, we have a compact root and a non-compact root, root. So this is what they compute. Actually, by a theorem of Schmidt, what they showed, you can show that for discrete series, this number turns out to be 1. So if this is 1, actually, then from Schmidt or Moscovici, what it tells you, what is the greatness about this theorem? It tells you we can use some geometry to compute. It's really related the Planck-Liouville measure, the formal dimension of discrete series representation with the geometry which is given by this term. Okay, so this is what this result tells you. So this one I can view it as the lowest. I will explain later, lowest K-type of this discrete series representation H pi. Okay, then so this one always equals to 1. So that is to say every discrete series representation of G, it contains a lowest K-type, and the multiplicity of this lowest K-type always equals to 1. So that's why this one is just 1. So what you are really compute topologically is the formal degree or Planck-Liouville measure for the discrete series representation for this G. Okay. So I wanted to say a few more things about this identity. So this, as I said, this is that for discrete series representation, it has a lowest K-type, and the multiplicity of this lowest K-type equal to 1. In fact, this result has been generalized by a very beautiful theorem by Vogel, which is also one of our motivation of this project. What it shows is that every irreducible representation with real infinitesimal, every irreducible tempered with a real infinitesimal character has a unique lowest K-type and with multiplicity 1. So what is the tempered irreducible representation with a real infinitesimal character? This corresponds to, in fact, at this end and this 2 dot and this all discrete series representations. So this is a nice thing. For example, if it's discrete series representation, this one tells you this one equals to 1. But Vogel generalized this result from discrete series representation to or irreducible tempered representation with real infinitesimal character. So for example, if it is spherical representation for G, then its key fixed part always has a multiplicity 1. So this is one special case for this theorem. So this theorem is useful because this one is play an essential role in proving this Mackey bijection. This is okay. Now I'm not going to talk about that. All I'm trying to say is that this is a very beautiful and nice theorem. Okay, so that I will get back to this. So this is our motivation. But any question? Okay. Okay, so what I on this board tells you, we can use the index theory to compute the Planck-Level measure for discrete series representation. So a natural question will be, what if there's no discrete series? When G has no discrete series representation. For example, G equal to SL3R or L equal to SLNC, and in complex semi-simple Lie group, there's no discrete series. In that case, that L2 index, of course, you can do the formulate same thing, and the L2 the index, no matter how regular this lambda you choose, this one always equal to 0. This is not surprising because from Atiyah-Schmidt, Komos-Kovic, we know the L2 index equals to the formal dimension of the representation. If it is no discrete series, its formal dimension will be 0. This Planck-Level measure at one point will be 0. So you compute what you get is just equal to 0. But nevertheless, since we are non-commutative geometry, this is not a problem because although the L2 index vanish, but we can know this operator, this D as the element is non-zero if we view it as the element in the K-series of reduced C-star algebra of G. So no matter this group G has discrete series or not, this one will be non-zero. In fact, this is the famous, this group, K-series group, is isomorphic to the representation ring of its maximal compact subgroup. This is known as the famous Kohn-Kasparov isomorphism, which is proved by Wasserman, Lafogue, and later generalized by Eschenhoff, Shepard, Nest, and many people contribute to this proof of this theorem. Okay, so that is to say, if the index live in here, then as non-commutative geometry, we can construct some higher cyclic co-cycle to detect. If it is non-zero, we can detect some information from here. Okay, so far everything is nice. But now let me tell you our motivation or our goal is that we wanted to go beyond K-series or index theory. Why? Because that Atiyah-Schmidt provided you a very nice way to detect or study discrete series. In fact, Atiyah-Schmidt, one application is that Atiyah-Schmidt, they geometrically realize discrete series representation of G as the kernel or index of some Dirac operator on the symmetric space. And this Kohn-Kasparov tells you we can use the K-series to detect some component of the representation, even there's no discrete series. But it has a defect is that this K-series at one side is very nice, very beautiful. You have all the index series machinery, but it can detect all representations. For example, in the SL2R case, yes. So for this is known as the spherical representation. What is spherical? Spherical representation for G means that those representation has a non-trivial K-fixed vector. So its K-invariant part is non-trivial. So no matter what, so that is true. In any case, the K-series can never see spherical representation. So what I'm trying to see is that if you use the K-series, it's like wearing in a glass. So you can look at wearing this nice glass. You can look at this tempered dew. You can say you can get a very nice picture. You can detect many things, but there's always some representation you cannot see. And the goal of this project or of my talk is trying to tell you we want to see other representations which cannot be detected by the K-series or index series. By the way, those representations is contained in the theorem of Vogel. So that's the background and the motivation of my talk. Any question? And the next I'm going to tell you, in order to go beyond the K-series, how do we compute and what kind of information we can get. Okay. So now I will leave this here. Okay, so I will start with, in this case, I will start with a V mu to be a representation of this maximal compact subgroup K. So as before, with this V mu, we can formulate a G equivariant vector bundle E mu. Just this one. This is a G equivariant vector bundle on the symmetric space G mod K. And the Hilbert space I'm going to consider is L2 of G mod K of E mu. This is, for example, if you take this, for example, if this one is a trivial, the space, Hilbert space I'm going to consider is just all the L2 functions on G mod K. Okay, we know that the point here is that there's no spinor bundle. We don't need spinor bundle. The point is that we want to get rid of a spinor bundle because we wanted to go beyond the K-series. We want to go beyond the index series. For example, if you wanted to study or detect spherical representation for G, you cannot use spinor bundle. So we just begin with any arbitrary equivariant vector bundle on this symmetric space. Okay, what do we do? And next, since there's no spinor bundle, of course, there's no Dirac operator. But that's okay, because although we don't have a D, but we have something also very good. So I'm going to let this delta of G to be the Casimir of G, which is element in the center of enveloping algebra of G. So that in a special case, if this E, for example, let me make one remark here. If the vector bundle you choose, say E mu E, is really, if you are in the Atiyah-Schmidt case, or in that case, if it has a spinor bundle, the bundle where you do have a Dirac operator D, in that case, D square is just this envelope Casimir of G minus Casimir of K. And this one acts as a constant because you fixed a K type. So what I'm trying to say is that in this more general setting, although we don't have D, but we have something like a D square. So that is something we are going to deal with. So we are going to work with the D square where when the D there's no D. Actually, we are going to take the Casimir. There's more in the center of, there might be many other elements, but we are just working with the Casimir, which is a quadratic one, like xi, yeah. Yes, yeah. So that one plays the role of the Laplacian. Yes, yes. But in fact, the formula the main tool we are going to use, in fact, makes sense for any element in the center. Yes, okay. So the key point is that while we work with the Casimir, the point is that Casimir as an operator acts as a constant on every irreducible representation for G. Now this is, and now let me tell you the main machinery I'm going to use today. So since I have no D, there's no index series, so there's no index formula. But for this Casimir element, we have something. This is the formula. Instead of the Atiyah-Singer index theorem, I'm going to use is a formula given by Bismuth. So Bismuth, by studying hypoelliptic operators on the symmetric space, Bismuth developed a geometric index formula for not elliptic operator, but for hypoelliptic operators. So I will write down what the formula look like. So the formula look like the L2, the trace of, we consider the heat operator, this of G. So you can see this is really like what we did in the index theory, the index theory. We consider the heat operator. If you this lambda, the Casimir is given by d squared, then you take the trace. But so between compute this one equals to, okay, I will write down the formula. Integration over the Lie algebra of K, and this is the A hat class. If you are index theory people, everyone like A hat class. So A hat class of adjoint of x on the p pot over A hat class of the joint action x on the k pot times the trace x on the v mu. This is the v mu is the irreducible k representation where we start of e to the minus x times e to the minus x squared. This is the Gaussian term times dx. Okay, so this is the Bismuth formula. So this is the, I will view it as the index formula for hypoelliptic operators. So that is to say, although this one has no d, but there still exists some geometrical formula for this trace. And it's not surprising since there's no spinor bundle, this one definitely depends on t. So this is the main difference between, as an index theory, if you have an index theory for elliptic operator, you compute its heat kernel, then the number should be independent of t. That is the point of the index theorem for elliptic operator. But it's hypoelliptic. This number definitely depends on t. Okay, so that what this formula look like. I will just rewrite it in a more explicit way. So this is the integration of. Oh, that's I guess there are some other people know.
This is what emerges from such an analysis. Formula formula.
Oh, yeah, thank you. Well, that is not for t, not for t. Yes, yes, yeah. Yes, so actually in this whole series of hypoelliptic, I think on Wednesday, Omar will give a talk on this hypoelliptic. So that is another parameter B. That is the short-term behavior and long-term behavior. So that is come from the de Rham theory or index theory on loop space. I guess this is where this formula idea of this theory came from. Okay, so that I'm going to write down. So this is A hat class as a geometer. Everyone like A hat class, but I will write it down more explicitly. So we can use the wild character formula to rewrite this one in an even more explicit way. So this one can be written as integration over t. T is the maximal torus for maximal compact subgroup K. And this is the polynomial term. This is for all the positive root of alpha x, and then times all the compact root of some sinh function of alpha over 2x over of all non-compact root sinh function of over 2 of x times e to the minus x squared plus 2t plus some shifting mu plus x, mu of x and dx. So that is to say, this is what I'm going to use. This is easy. Using wild character formula, you can reduce Bismuth formula, which is integration over the algebra K to the integration over the Lie algebra of T. So this is a polynomial term. This is some sinh term over some sinh term. Okay, let me make one comment here. Is that if you think about this formula, it makes sense even when the group G is just compact. If the group G is compact, the manifold you get, symmetric space, just K mod K, will just get a point. But so on one hand, the manifold is just trivial, it's just a point. But the right-hand side of the formula is still non-trivial. You just don't have this denominator term because denominator term come from the non-compact root. So what I'm trying to say is that this formula is already non-trivial and interesting even for the case when the group G is compact. How do you relate it to this one? Because if in a compact case, when the G is compact, this is just what you are going to compute is a vector bundle over a point, which just a dimension of an irreducible representation for K. On the right-hand side, you have something non-trivial. But how to relate it? They are related by wild dimension formula. But this makes it more interesting when it has a non-compact term. Okay, so this is the main tool. So this in Atiyah-Schmidt, they use L2 index formula. In Komos-Kovaci, they also use this McKean-Singer index formula. In this case, this is the index analog, the index formula I'm going to use. I'm going to use this one to compute it, and I wanted to extract some representation theoretic information from here. Okay. Okay, now let me tell you our key observation. Okay, on one hand, this Bismuth formula is great. It's geometric. It's look like this one, but I have to tell you, formula like this one is still very difficult to compute. First of all, this integration depends on t, and if you want to know what it is on one side it's an explicit formula, but if you want to do computation, then you don't know where to start. It's still non-trivial. But now let me tell you our key observation is that as t goes to infinity, this formula, it is more computable. What I'm going to show you is that as t goes to infinity, why we can really compute this term. So if we can get something non-trivial, then you can ask, we can get some dominant term. And those dominant term is more computable. Even with this will provide a different viewpoint or different computation for Atiyah-Schmidt in a different way. But we are going to use Bismuth formula to compute that. And of course, representation on the other side, on the representation series side, you can ask that as t goes to infinity, which representation will contribute to the dominant term. In the discrete case, when the number is regular or mu is regular, it won't surprise you that it will be the discrete series, as in the Atiyah-Schmidt case, contribute to the dominant term. But as I said, the whole point is why we wanted to use Bismuth formula is that we want to go beyond K series. So that is to say, we can ask the same question when this mu is a singular. For example, when you take mu to be trivial, you can ask which representation will contribute to the dominant term. This is what I'm going to tell you. Okay, so in fact, okay, let's begin with the simplest case. How do we compute it as t goes to infinity, and why it's computable as t goes to infinity? So here, step one is that as t goes to infinity, this integration is the integration over the Lie algebra of t. But the first simplification is that if we only want to compute the dominant term as t goes to infinity, you don't have to integration over all t. So that's, for example, I can tell you, for example, when mu, the first case is that when mu is regular. Again, I will postpone the definition of a regular in a moment. When it's regular, roughly speaking, it says that mu is in a very interior part of some positive wild chamber. This is, you have to make choice of a positive wild chamber. So the first simplification is that instead of doing the integration over all, you can the algebra T, you don't have to. You can just restrict yourself to a cone, to a positive wild chamber. So that one can be reduced to this one. So C stands for the positive wild chamber determined by this mu, this highest weight of K representation you begin with. Of this, this is the polynomial term, alpha of x, and we have this one, sinh of alpha over 2 of x. This is over all compact, positive compact root. This is over all positive non-compact root. This is minus x squared for 2t. This is my positive well chamber C plus mu of x of dx. Okay, so step one is that we can restrict ourselves to one positive well chamber determined by mu. And why this is why this one will is good, because that if you look at Bismuth formula, this is a polynomial term, which is not bad. This is a Gaussian term, which is not bad. What causes upon what we don't like is this term. Okay, but if you restrict yourself to a positive well chamber as t goes to infinity, basically it tells you what is the asymptotic behavior, or what is the dominant term for this term and this term. So what this one is, if you sit inside in this well chamber as t goes to infinity, one thing you can simplify is that you can replace this one by e to the rho k of x, because just asymptotic. So the behavior of this one is more or less like this one. And for this the numerator term, this one is just e to the rho n of x. Rho n is the half sum of the positive non-compact root. Rho k is the half sum of positive compact root. So that if I can replace this term product, which is annoying, by some single term like this one, we can replace this one by some single term like this one, then that will be great, because I can, let me just change, because we can do this simplification. What we can do is e to the minus x squared over 2t plus mu plus rho k minus rho n of x times dx. What I'm trying to say is that when you restrict yourself to a positive well chamber as t goes to infinity, if you are only interested in the dominant term, this long-term behavior, then the computation of Bismuth formula, which is difficult, can reduce to compute integration like this one. The reason is that where these two terms just come from the simplification of these two terms. Okay, this is good, but this is not over yet. Tell you. Now I'm going to tell you, because this is a regular case, what I'm going to tell you is that we can actually provide you a different way to compute or recover a Schmidt's computation or an Komoskovic's computation, and which can be also generalized to singular case. Okay, any questions so far? So we're just going to compute this one. And let me make one remark. What does this term look like? Think about it. This is a polynomial term. This is some like a shifted Gaussian integration. So you might think this is easy to compute. In fact, still, it's not easy to compute. Why? Is that you are doing an integration over, not over Rn, but over a cone. So here's what I'm trying to say, is that Gauss integration, there's a formula, it's easier to compute over a Euclidean space. But if you want to compute some Gaussian type integration over a cone, this is already non-trivial. This is something related to called McDonough meta integration. So this is basically, roughly speaking, essentially, this is tells you how to compute some Gauss integration over a cone. But since we are only interested in the dominant term, we can do further simplification of this one. This is what I'm going to tell you now. So this is step 2. What we can do is that we can just replace Tx by Tx. We just rescale this cone. Then let's see, what do we get? The formula, what do we get, will be integral over this cone of polynomial term as before. This is e to the minus x. I will denote for convenience, I will just denote this one by lambda. Mu plus rho k minus rho n by not lambda. Okay, so this is will be x minus lambda square t over 2 plus t times lambda square over 2 times dx. This is just an easy trick, just replace x by tx. But why this one is helpful to us? Because that this is just a term independent of x. This is the Gaussian term like this one. This is the polynomial term. So that in the regular case, so now I can tell you what do I mean by regular. Regular means that if you have a mu starting from mu, sitting inside some wild chamber, and you can plus mu plus 2 rho k, which is give you still, this is one point which still lies in the positive interior of positive wild chamber. But if you consider mu plus rho k minus rho n, this what I mean by regular, it means that after you minus rho n, it still lies in the interior of wild chamber. This is what I mean by regular. If it is a regular, as t goes to infinity, think about it. The key property of the Gaussian integration is that as t goes to infinity, this term play like a delta function. So that is to say, although you are doing integration over a cone, but as t goes to infinity, you can really restrict yourself to a small neighborhood of this point, which is in the like Rn. And we can reduce this integration of Gauss integration over a cone to an integration over a Euclidean space, because this really play like a delta the function as t goes to infinity, what this one equals to. So this one really play the role of the delta at lambda. So when you do integration, you just replace x by lambda. So this is what you will get. This is this term of alpha of lambda times e to the power t of lambda squared over 2. So this is what the formula look like as t goes to infinity for the regular case. And what is the representation theory information you can tell? In fact, what this one is. Let me see if I still have the formula. Okay, maybe I erased, but what I'm trying to say, this one is in fact the Planck-Level measure. For the discrete series. And this lambda, in fact, is the Harish-Chandra parameter of the discrete series representation. So what I'm trying to say is that using Bismuth formula, the computation of discrete series case can be really reduced to some localization for the Gaussian integration. And you compute it in this way. Okay, now you may wonder, okay, so we just provide a different way to compute the discrete series, or to provide a different use Bismuth formula compute the problem considering Atiyah-Schmidt, Komos-Kovaci. But the point is that actually why we use Bismuth formula is that if you go think about it, everything still makes sense when you go beyond the discrete series. That corresponds to the singular case. Here, the regular means that, in fact, you begin with one representation of k with highest rate mu. If mu plus rho k minus rho n still sit inside this interior of wild chamber, this one is exactly the discrete series, the Harish-Chandra parameter given by discrete series. But in general, if you, as I said, we can start from any arbitrary mu, which can be singular. In that case, the Bismuth formula still makes sense. That's why the reason or motivation why we wanted to use the Bismuth formula to attack this problem, which allows you to go beyond K theory, because the machinery we are using is not an index theory for elliptic operator, but for hyperelliptic operators. Okay, now what makes it interesting is that now let me tell you is that singular case. Singular case corresponds to the, I will draw you a picture. We begin with a mu, which is inside this interior of wild chamber, and we can shift, then we shift it by mu plus rho k, which is still lies in the positive wild chamber. But if you mu plus rho k minus rho n, you may fall outside this wild chamber. So in that case, the integration, I'm trying to stay here. So this part is still good. The point is that this lambda will be like this. This is lambda. So you are doing a Gauss integration with the shifting outside this cone. If it is outside this cone, if you want to take t goes to infinity, what happened in the regular case does not work, because in the regular case, you can reduce to a neighborhood of this point of lambda. What you get is Gauss integration over Rn. But since this lambda is for outside this wild chamber, so what you will get? This one, what you get is that this is another Gauss integration over a cone. What you get is that you have to goes to the lambda will be here. The projection of mu, so this lambda will be the projection to the cone of mu plus rho k minus rho n. So that's the integration. What do we get? Will be something like some constant times t to the some power of e to the power of t of lambda square over 2. But now the lambda is given by the projection of mu plus rho k minus rho n. So this is something you will get. So what I'm trying to say is that in the singular case, this formula still works. When you do Gauss integration, if you want to compute it, then you cannot really do the localization. This is more subtle here, but yes, this as t goes to infinity. Everything only, every step I did only makes sense when t goes to infinity. Every simplification I did is only valid when I let t goes to infinity. Okay, in the last 5 minutes, I will explain to you as I said, in the beginning I said the motivation is that we want to go beyond K theory. I promise I want to go, for example, at least I will show to you how do we detect spherical representation. I want to show you where this term came from. Where this term came from Bismuth's formula. This is what I'm going to show you in the last 5 minutes. Okay, so here I hope I convince you in the singular case, things are different, but things are different. Okay, here's one theorem. What we can show is that this is not really a theorem, just some observation or some what we can show is that as t goes to infinity, so we can see this mu plus rho c minus rho n lambda could be singular. It can be on the wall of the wild chamber. It could be for outside this wild chamber, which will no longer be discrete series case. But in any case, what we can say is that as it goes to infinity, we can, I'm trying to be vague about this theorem. We can reduce to the most singular case. What is the most singular case? That is correspond to case lambda equal to 0. After you do projection, you get 0. This is actually this one has a name. This is known as a small representation. In particular, all spherical will be small representation. Small representation after Vogel. Okay, this one is good because if you are following Harshchandra's work on representation theory, or if you wanted to realize the representation theory, a representation of G, you can begin with a discrete series representation for some smaller group, and then you do parabolic induction. So that is to say, from the viewpoint of Harshchandra's work or Zuckerman's work, the discrete series is like the building block of representation of G. But if you follow Vogel's construction, say cohomological induction, the building block will be small representation instead of discrete series representation. So small representation means that those cases correspond to lambda equal to 0. Okay, I will finish my talk with one last computation for SL2R. How do we get this one? This is a small case. So here, in a general case, we can always reduce to the most singular case. I'm just going to finish my talk with one computation about the most singular case of SL2R. When G equal to SL2R, K is a billion just given by SL2. We wanted to deal with the most singular case. Why not we just take V mu to be the trivial representation of K? Trivial K representation. So in this case, the Hilbert space we consider is just really G mod K. Okay, the mu in this case, mu equal to 0. Okay, Bismuth formula tells you the computation will be integrated over T, which is just R. In this case, it's dimension 1 of X over sinh X, because in this case, it has only one non-compact root, no compact root. So the denominator has no sinh function. There's only one non-compact root, so we have only one term in the denominator times e to the minus x squared over 2t. No shifting because mu equal to 0. Okay. So this is what Bismuth formula tells you for the singular case. Okay, how do we do computation here? So what we can do is that we can apply Fourier transform to this term. Fourier transform for r, we can rewrite this one as integral over r over another r of 1 over sinh function of x times y times e to the power of minus t y squared over 2 times dy over dx. Okay, so x times e to the power of minus x squared over 2t, its Fourier transform is given by y times minus t y squared over 2. So this is just a Gauss integration. You flip t from the denominator to the numerator. Okay, what do we do next? We do a Fubini theorem, which you can check. We are okay to do this. Fubini theorem, we can swap x and y. So we, oh, sorry, so I forgot one term, plus ixy. This is the Fourier transform. Okay, and now the key observation or one interesting formula is that the Fourier transform of 1 over sinh function of e to the power of ixy just equal to what this one is. This one, in fact, just equal to hyperbolic tangent of pi y over 2. So that if you apply Fubini theorem, you integrate over x first, what you get is the integral over r of y times hyperbolic tangent of 2y over pi y over 2 times e to the minus t y squared over 2 times dy. So this one is the Planck-Level measure of a spherical. So what I'm trying to say is that in the singular case, how do we get, because in the singular case, if you wanted to compute this, the dominant term actually, or this do the integration, there's no discrete series. What you get should be a family. And this one is related by the Fourier transform. What do you get? This is how do we recover the Planck-Level measure for the singular representations. So this is, I will view this one as maybe an analog of the discrete series representation to those representations which are not in the K-series. So this is then Bismuth formula. The Bismuth formula provided you a way to compute these things. This is how do we recover the representation theory information from this computation. And now, last 1 minute, I will say that, of course, you say, this is just a SO2R case. This is too easy just because there are very few there's only one root here. It's too simple. But in fact, what we can show is that the general case can always be reduced to the case of A1 or B2. So that is rank 1 case and rank 1-2 case. If you compute these 2 cases, I didn't show you the computation for B2, say SP4, but the computation is same here, and you can reduce the general case to product of A1 and B2. This is how do we recover Planck-Level measure for the singular case. And I think I should stop here. My time is up. Thank you.